Okay, so now what we are going to look at is, for the next few slides, it will be little theory, but I'll try to make it as reasonably uh, interesting and practically applicable. And after we go through the theory, we will look at some algorithms, which will be after which everything will make sense. But to begin with, it will be little theory. Let us see this. Okay. Um, Now there is a set of problems. Like when I say problem, I mean things like the traveling salesman problem, Hamilton circuit problem, minimum spanning tree problem, shortest path problem, coin collection problem. So those are the problems, and for each problem we saw one or more algorithms in this course, right? All right. So we can call a set of problems as what is called a class NP, means non-deterministic polynomial. That's what NP means. If we can go through these two steps, we can first determine a solution for that problem, okay, in polynomial time. Now the problem could be again optimization decision problem, and we could determine or at least guess a solution for the problem in polynomial time. And then the second step is you can check the correctness of the solution that you obtained from the earlier step in polynomial time. Now for the Dijkstra's shortest path problem, that's what we went through. We have a shortest path problem and we came up with the Dijkstra's algorithm, right? So we determined actually, we did not guess, we actually determined the optimum solution, the shortest path tree, starting from the source vertex in polynomial time. It was E log V. And then we went through the proof of correctness of the algorithm. So we went through all these things for the shortest path problem. Similarly, the minimum spanning tree problem, we went through both the steps. Now, when we can actually determine the solution, the optimum or decision version in polynomial time, then we can say the problem actually belongs to a class called P. Now this class P is a subset of the class NP. So it is going to look something like this. This class P is a subset of the class NP. That means all the problems we have seen so far in this course fall actually in the category of class P problems, because for all those problems we were able to determine an optimum solution or decision solution in polynomial time, and that solution, that algorithm that we came up with, is deterministic. That's the most important keyword. Why it's called why we can say all the algorithms you have seen are deterministic algorithms. So what do you mean by deterministic algorithm? So an algorithm is said to be deterministic if for all inputs it's guaranteed to give you what it is designed for. So that means the Dijkstra's algorithm is deterministic because given any graph, it's and the starting vertex is guaranteed to find you the shortest path tree starting from the vertex. Similarly, the Kruskal's algorithm is deterministic because given any graph with edge weights, it's guaranteed to find you the minimum spanning tree, because we went through the proof of correctness. Remember, for any graph, it's guaranteed to find the minimum spanning tree. Similarly, the breadth first search algorithm is deterministic because given any graph, it is going to be able to decide whether the graph is bipartite or not. So all the algorithms we have seen so far are deterministic. Means for once this is designed for a particular problem, it doesn't matter what input or what graph you work with. For any graph, it's going to give you what it is designed for, a minimum spanning tree or shortest path tree or all path shortest path or whatever it is for. Okay, even the coin collection problem, given any grid with some distribution of coin values, any grid or any distribution of coin values, that algorithm, the dynamic programming algorithm we came up with, is guaranteed to give you the maximum coin value that could be picked up. Okay, the total value, total maximum value. Similarly, all those problems in dynamic programming and even the greedy strategy problems, given any distribution of the symbol fraction values, you are able to find the Hoffman code. That is also optimization problem. Similarly, the other problems, everything I've seen so far are deterministic problems. Alright, so why I emphasize on the word deterministic? Because in this module we are going to focus on what is called non-deterministic algorithms, or problems for which there can be only non-deterministic algorithms. Okay. So what I mean by a problem for which there can be only non-deterministic algorithms that can run in polynomial time. So this traveling salesman problem is an example for that. This is a problem for which all the algorithms available so far can give you only non-deterministic solutions in polynomial time. So they are polynomial time algorithms. Again, what I mean by polynomial time algorithms, they can run, the time complexities are polynomial, v square, v log v, all these things are polynomial, but they are not deterministic in nature. So what I mean by not deterministic, that means let us say I come up with some algorithm for the traveling salesman problem. Okay, for some complete graph with some distribution of edge weights, it is going to give you a minimum weight tour, and you can always cross check by writing down all possible tours, and if the algorithm is able to find a b c d a in say v square time complexity, that is a polynomial time algorithm that gives you the optimum solution for this particular complete graph of edge weights. Again, you can cross check, that's the second step actually, cross check by the correctness of your solution. So you can write down all the possible solutions and check this is the minimal weight 2. Now, what is it not deterministic? For some other complete graph with some distribution of edge weights, that same algorithm may not give you the minimum weight 2. It may give you a tour whose weight is larger than the minimum weight. That algorithm may not be able to find you the minimum weight 2. So that means for a particular problem, say the traveling salesman problem, you have say an algorithm, you have designed an algorithm. That algorithm was designed to give you a minimum weight 2 for any graph, for any complete graph with arbitrary edge weights. But that algorithm is not guaranteed to give you the minimum weight tour for any arbitrary complete graph. For some complete graph with some distribution of edge weights, it's going to give you the minimum weight tour. But for some other complete graph with distribution of edge weights, it may not give you the minimum weight tour. So that's what we mean by non-deterministic. Sometimes it gives the optimal solution, sometimes it does not give the optimal solution. So you may think why we need to go for such algorithms. The thing is, for the traveling salesman problem, all the algorithms available so far are only of that type. There is no algorithm that developed so far that gives you always a deterministic solution, again in polynomial time. So why I say deterministic solution in polynomial time? See, for some complete graph like this, I can always write all these tours, all possible combinations of vertices, right? But that's a brute force approach and takes exponential time. It's not polynomial time. It will take exponential time to come up with a polynomial time, to come up with a deterministic solution. So if you want a deterministic solution, an optimal solution, or even decision solution in polynomial time, for such problems you don't have a deterministic algorithm. Okay. So similarly, in the deterministic case, you also have the same problem. For the Hamiltonian circuit problem, is there an algorithm that can always say an S answer if the graph has a 2, and always say a no as the answer if the graph does not have a 2? The answer is there's no such algorithm that can guarantee the right answer. So that means you have algorithms. If you run that algorithm on a graph, it may say no, the graph does not have a 2, but the graph may actually have a 2. It may not tell you the other way. If the graph does not have a tour, it may not say the graph yes has a tour. It won't do that. but it could give you what is called false negatives, in the sense that the graph may have a tour, but it may say the graph does not have a tour. Okay, so that's where the non-deterministic nature comes. So there are a lot of problems, you'll be surprised, that are of this category, for which there is no algorithm that can give you the deterministic solution in polynomial time. So if you want a deterministic solution, you have to go for an exponential time for such problems. So such problems are said to belong to the class NP, and they are outside this class P in this distribution. So they all fall in this category NP and not in the class P. Of course, P is a subset of class NP. If you have determinism, then that problem is in the class P. If you have non-deterministic algorithm that can give you optimum solution or decision solution in polynomial time, that belongs to the class NP. So that's the difference between P and NP. If you have any questions, you can stop and ask me in the meantime. So let me just quickly save this video.